is come up front. Okay, so basically gave you a summary of how various conventional techniques work starting from the mean field plus fluctuations, and that is basically the framework of how to deal with phases which order. And so, I listed out some of the things as to what are the ingredients that goes into these calculations. So ended up with this comment and this last few minutes where I discussed what happens if you do not have these crutches of symmetry breaking. It might be because either symmetry is not there at all, and then it is not meaningful to ask the question whether you can break the symmetry or not. And then there can be other situations where you have a symmetry, but the system does not take the symmetry breaking route. Okay? So, in either cases you cannot use any order parameter based description to try and understand these phases. So, at this point we are not even sure how to describe these phases, but what I ended up with in the morning is that there is a precise way to try and ask whether there are different phases, in the sense that if the ground state wave functions, many body ground state wave functions of gapped systems can be analytically connected, adiabatically connected with each other, then there is a meaning to saying that they are they belong to the same phase, whereas if they require a closing of gap at least once, then they belong to different phases. Now, as was pointed out, is that I was writing down Hamiltonians like H1, H2, and basically H of lambda, which was lambda into H1 plus 1 minus lambda into H2. This is a specific form of interpolating between the two Hamiltonians, but the ideas generally go quite are much more general. So, I have the H1 and H2. These are two Hamiltonians in an infinite dimensional parameter space of coupling constants of the type of Hamiltonians that I wrote down, but none of them have any symmetry, or if they have the symmetry, they are the same symmetry group. And I so this is an infinite dimensional space with different axes being different coupling constants. Now, I can pick any third point H3, which is like in this case some value of lambda. So, I can think about such intermediate points at all these points, and each of these points would represent some Hamiltonian of the system. And I said that if so this is one example, but there may be many other examples of doing this thing in a many parameter way. Okay? So what I said is that whatever I do, all these paths of Hamiltonians, okay, different paths, H3 prime. So, all these paths, this Hamiltonian has a gap. Okay. Oh, okay. So, so if it always has a gap, then it is the same state. I can adiabatically connect these things, but this, as you realize, it's a very bad way of putting things. I mean, I check for one path, I check for a second path, but there are infinite number of ways I can interpolate between the two Hamiltonians. How am I sure that these are never going to, I'm never going to close the gap, or I'm always going to close the gap? Okay? So, this way of putting things, though makes it more quantitative than very qualitative questions like how do I define phases, how do I characterize phases in absence of symmetry, but it's not much better. So we want to make this more quantitative so that we can make some do some calculations to identify a number or a set of numbers which allow us to say whether it is possible to deform from one Hamiltonian to another, the ground states of these two Hamiltonians without closing a gap, or gap closing is necessary without going through this infinite set of calculations, which is of course not possible. Okay? So, that is one thing that we want to do. And so, since so this would lead us to the physics of quantum spin liquids. Actually, quantum spin liquid is a part of a much larger problem, in the sense that there can be a large class of phase which have this property that they are not distinguished by symmetries, but something else. So, that something else is basically quantum entanglement. Okay. More precisely, long range quantum entanglement. Okay. And this is what we would try and study. And for spin liquids and many of these states, the common feature of this long range quantum entanglement would be, at low energies you get non-local excitations. In the worst cases, you do not get quasi-particle excitations, and to describe these non-local excitations, you need gauge theory descriptions. And one of the fallouts is that if these Hamiltonians have some symmetry which you do not want to break, and you are in this long range quantum entangled state, the quantum numbers carried by these excitations, the symmetric quantum numbers carried by these excitations, this non-local excitation, can have fractional values. Of symmetry. So, these three are basically outputs of this presence of long range quantum entanglement, and this is what we want to cover in this lecture and the next two. Okay? And so, how do we do this? So, historically there has been several approaches. The oldest one, as far as I understand, is trying to devise a mean field description for these systems. And this is where Professor Bhaskaran, who works here, contributed a lot along with Phil Anderson and other people in 80s. So, these goes under the name of Parton mean field theories. Okay. This is not what we are going to do, but we are going to do slightly a version of this, which is from where you would probably very easily connect to the Parton mean field theories. So, there are more mathematical ways of doing this, which has become clear of late. Basically, understand classify all possible symmetry fractionalization, and mathematically this turns out to be related to understanding various cohomology groups and projective representations of symmetric groups. So, that's and write down consistent long wavelength low energy field theories consistent with these symmetries, very similar to what we do in Landau-Ginzburg approach, but with this extra twist that symmetry may not symmetry may act in a very funny way. Okay? There is a third approach which is much more transparent and easy to introduce, which has basically come about because of this very influential set of works primarily by Kitaev and some other people, is to try and introduce exactly solvable models which may not be something that you would immediately encounter in experiments, but it contains all the essential features of what you might possibly encounter in experiments, and but with this additional simplification that you can do calculations in real time, in the sense that I will be doing them on the board. So to introduce some of these ideas, I will take this third route of exactly solvable models. Of quantum spin liquid. Okay. So there is a catch to this. The point is that exactly solvable models contain certain features which are not very general, in the sense that you destroy the exact solvability and those features go away. So one has to be very careful about about understanding the features of exactly solvable models. But since this work started in 1998, I think at least the paper appeared in 1998, the preprint, and since then we have a fairly good understanding of which features are robust and which features are not robust. Okay? So this is what I'll do. Okay, and try to connect up to these two other features. Okay, good. Sorry? Yeah.
Answer actually all questions of
all universal properties. Okay? So not non-universal numbers. I think I won't even attempt to address non-universal numbers. This is not the right framework to do that. And in many cases, we have very limited understanding of how to address non-universal numbers. Any other question? Yeah, those are things that wait for the next. Yeah. 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 I'll discuss this in great detail. So I'll basically address these questions in great detail. I'll quote some results about quantum entanglement and argue how to understand them, but some of them are numerical calculations, so I cannot reproduce in real time.
You just said that if the gap never closes, then you can always interpolate and thermodynamically connect those two points.
Right.
So what if in between somewhere there is a phase transition, like
so
say
the gap has to close for
no,
a phase
I say the gap doesn't close, but still there is a phase transition.
You cannot have such
no,
things.
say for some level crossing is happening.
Yeah, so the gap would close, some energy state will come down. Anything else? Okay, good. So this is the plan. So I'll take this exactly solvable model and explain these features. And you would soon realize that whatever we discussed in the first lecture, all this mean field theory in the form that is discussed does not apply to this class of systems. Okay, so so since Diptiman has already discussed Tori code, let me write down a few things on about Tori code, which is the exactly solvable model I'll concentrate on. And instead of going through his discussion once more, let's have a question answer session. You can ask me questions, I can try to answer to clarify things. I'll go over his points, all his points. Let me just fill out some notes for doing that. Okay, just to be consistent with the okay. So, I have the spins sitting on the bonds, spin halves. I won't draw everything. So, I will erase this, but just keep this in mind. So, the Hamiltonian is so, AS is really the same thing, the product of the sigma x's on these 4 sides connected to a vertex, and BP is this operator. Okay. So that is the Hamiltonian. So, the ground state, which we can solve exactly because all these AP and AS and BP commute, is basically product over I, product over S, 1 plus AS by 2 to all up state. This is on a open boundary conditions, infinite plane. Okay. So, before we go on further, let us draw what this ground state looks like. Okay. So, this the state that is here is all up state, like all these spins are up in sigma z direction. Okay. So let me denote it by that nothing here means that all the states are up. What does an application of AS does? It's just, so suppose I apply to this AS. If I draw this lattice on the dual lattice, this loop on the dual lattice, which is obtained by joining the midpoints of these placates, and draw this loop, it basically flips all these spins sitting on this loop is basically flipped by this AS term. That is what sigma x does to sigma z up. So, AS on this would give rise to this thing. This basically is a shorthand for denoting that everything is up except for this. Okay? But if I expand this thing, there would be series of AS, there would be AS prime, which can be connected or disconnected. If they are disconnected, I will get 2 loops. If they are connected, I will get a bigger loop. Okay? And this goes on. So, the ground state is basically this. We have all plus this loop can be anywhere. Then there are two loops, and so on and so forth. All superposition of loops, where loops mean that the spins that are on those loops are down, whereas the spins that are not on the loop are up. Okay. So, that is the structure of the ground state. So, if I go to any spin and basically try to calculate the expectation value of that spin using this ground state, so you can see that there is almost equal probability that this, that spin is not on the loop from this type of states. It might be this spin here, and there is equal probability that it is on the loop. So, the ones on the loop provide up expectation value of +1, the ones the ones that are not on the loop provide an expectation value of +1, and if it is on the loop, it is just -1 for sigma z operator, same for sigma x. So, if I right. So, if you start with all sigma x to be up, okay. So, you could start with that state and then act VP in the same way. Then instead of drawing this dual lattice loops, you would draw the direct lattice loops, same. The resultant state is the same. Okay. So, basically if I calculate something like sigma z I with this ground state, it's going to give me 0. There is no expectation value for this local operator. Okay. By the way, I forgot to make a point that I wanted to make. I don't know if Diman made it. So, this with this seems that there is no dynamics. So, what is the difference between this type of model and something like a classical Ising model? Okay. So, this is, as we would find that it has topological order and things like that, we are saying that it has Longrange entanglement, which is a purely a quantum mechanical property, because we often ask if there is no dynamics, what is quantum mechanical about the system. So, notice that these operators, though commute with each other, the Hilbert space is in terms of the spin halves. So, the primary operator, the Pauli matrices, do not commute with this Hamiltonian. Okay? That is very different from Ising model, classical Ising model, but these primary operators, the sigma z that are there. Okay? There is one set of operators that form the complete basis, which commute with the Hamiltonian. Okay? Fine. So, that is the comment. So, here the point is that you have these things and all these local observables are 0. You can calculate the 2-point correlator for nearest neighbor, it is a very small number. You can calculate all correlators, it would be exponentially decaying. Okay? So, there is no long range order, okay, with this state. So, then let me try to put forward another Hamiltonian, which I already said. Suppose it is the same system, but the Hamiltonian is minus, I do not need the minus though. Okay, where this gamma, this field is random. And not 0, otherwise random. Okay. So let's, yeah. Huh? No, not necessarily. Yeah, so as I said, the minus sign is not important. You can just write. Okay? Huh? Yeah, only x terms. You can put z terms, but it doesn't matter. It's just
classical model.
Yeah. So the point is this is the simplest Hamiltonian I can write to drive home the point that I want to make, and try with other Hamiltonians like the Ising model, transversal Ising model, or whatnot. Okay, more complicated things. Okay, so this is another Hamiltonian, the same Hilbert space. You can try to find out what the symmetries are. This has lesser symmetries, but you can amend this by putting this here making this site dependent and things like that, you can make all the symmetries to be same. Okay. So, what is the ground state of this? So, the ground state is something some random thing. So, whenever this gamma is positive, the spin, the corresponding spin is down. Whenever gamma is negative, the corresponding spin is up. In this, yeah, sorry. This is x basis, or you can also put this to sigma z, whatever, right? So, I have these two ground states and the corresponding to Hamiltonians. So, now from Diptymann's discussion, I will come to that discussion of charges in a moment. You know that the excitations for this Hamiltonian are gap. Okay? Similarly, if I think about excitations of this Hamiltonian, okay, suppose on the first site gamma is positive or negative in the and I want to flip that. Okay? I would have to spend an energy which is of the order of gamma of that side. Okay? So, the minimum excitation cost an energy of minimum of whichever gamma is. So, I have a whole series of gammas. I pick the site where gamma is minimum and I flip that spin, that is going to be the minimum energy. It is again a finite number, so it is gapped. Okay? So, can I use this argument to this system? I have two Hamiltonians, this and this. I do not break symmetry. I have gap spectrum. Can I use this? Are these two ground states same or different? Okay. Again, I pointed out that asking this question of trying to interpolate this two Hamiltonians is very difficult way of trying to answer this question, almost impossible. Okay? You cannot check all the Hamiltonians that is in between these two. So, we need a better way to do this. Okay? So, fine. So, what we are going to do is basically try to show that, not proof, but show that the right thing to look at is entanglement entropy and entanglement measures, of which entanglement entropy is one of the features that already is good enough to characterize these two systems, the difference of these two systems, and that is what we will do. So, just a brief detour. As you know that quantum systems like 2 spin half can be in a singlet state. Okay. You can try to think about what the entanglement is. So, to think about that, you introduce the density matrix, and then what you do is basically integrate out one of the degrees of freedom, say the second spin, and write down this reduced density matrix. Okay, and calculate the entropy from this reduced density matrix. This is very easy to do for this state, and you would get log 2. On the other hand, if you take a product state like this or the other one, you get 0. I think all of you have seen this in some form or the other. Okay. So, basically this entanglement, even though the state is perfectly correlated in the sense that if one is up, the other is up, or if one is down, the other is down, it does not have any entanglement. On the other hand, this looks like a completely random state in the sense that the first spin can be up and the next spin can be down or the other way around. It has a finite entanglement, but if you look at the on-site correlators, the one-point correlators or the average value of spins, it's not necessarily, it's not non-zero, it's 0. Okay, that's a singlet state. Good. Yeah, entanglement entropy. So this is called the entanglement entropy. This is all t equal to 0 calculations. Okay. Fine. Is there any question? This, I mean, yeah. So that's a measure. With this negative, you get this term positive. I mean, to define with a negative sign, you have to be consistent with that. Okay. There's a positive definiteness with this. Anything else? Say that again. No, this is a pure state. This is the state of the system. Okay. Right. So if I calculate the entropy of the total system, that's 0. The entropy of the total system is basically the same thing with not this reduced, but this net. Okay. So that's 0. So it's a pure state. Okay. This entanglement entropy actually captures the amount of this is bad word, but amount of quantum correlations in the system, okay, which doesn't have a classical part always. That's the idea. So a better thing to look at is basically this reduced density matrix. There are various measures. So entanglement entropy is one number that comes out of this reduced density matrix, but you can, this is a matrix, right? It's a 2 by 2 matrix in this case. Okay. So you can try to fish out other important things out of that matrix, and sometimes they are more useful rather than entanglement entropy. Okay. Say that again. Yeah, it's same as S21. You can show that, all those things.
There can be like correlations beyond entanglement also, for which this won't be a good measure.
No. Okay, I don't know the meaning of that question. Maybe you should explain that to me after the class.
Kind of like there can be quantum correlations without for some states when there is no entanglement also, kind of.
Okay, you should explain to that me that question after the class, giving an example. That way I can answer, but I don't. Okay, fine with this. So now instead of 2 spins, we are going to do this for this system. How do we do it? The way to do it, and I'm basically going to increase the scope of this type of calculation. Okay, I don't want to. It is okay. So instead, I have this whole system. I divide it up in the following way. I create a set of sites which unambiguously points out whether a particular site belongs to either this shaded region or this. The boundary sites I am going to include in the shaded region. Okay? So this is an unambiguous definition of which sites belong to which region. So I am going to call this shaded region as A and unshaded region as A bar. And then I am going to treat this shaded region as a first spin, which I am going to keep, and this unshaded region as a second spin, which I am going to integrate out. Okay? So, that is the straightforward generalization of these two spin thing. Okay? So, I will write down again the wave functions, the ground states either this or this, and carry this out. And here the tracing would be over A bar and okay, that is what I am going to do. Okay. So let us do it for this state first. What do you think is the answer? It's random state of this Hamiltonian. So if I calculate entanglement entropy starting with this state, what is the answer? Let me write it eliminating way. All in the x basis. Okay. Say that again. Loud. I cannot hear. 0, right? So is this answer clear to everyone why this should be 0? It's a product state. So just like this state, doesn't matter whether you integrate out this other degree of freedom or not. Okay? So if you do this starting with this state, the entanglement entropy for this state is 0 for this state. Okay? Is it clear? Okay. So what if I just add a few things like say take the first two spins and put them in a singlet state like this and do it at a time with few spins. Just superpose some state with a small amount of superposition. So I basically add some small number here and I add a few more states, superpose them. Okay? So if you wonder that that's not a ground state, you can basically add small terms like this, keep the major term, keep this as a major term and add a small term like this. Okay? And this is going to mix this with other states, but keeping these to be small. Okay? So what would happen is basically once you add these terms which are nearest neighbors, okay, let's stick to nearest neighbors, it would generate some type of entanglement between things which are close by nearest neighbors. So spins which are sitting deep inside this shaded region, they are getting entangled, but they are not getting integrated out anyway. But on the other hand, this spin and this spin, which are on the opposite side of the boundary, one is getting integrated out and the other is not getting integrated out. Okay? So they would generate some entanglement. Okay? So that's roughly how things turn out in this class of models where you add short range interactions. Okay? Where we know the results in the best, I mean, where we are most confident about the results. And so you ask how many such bits of entanglement are there, and you would find that that goes as the number of spins across the boundary, interactions across the boundary. It roughly goes as the length of the boundary. Okay? So if you add such terms, this number is no longer going to remain 0 and would be replaced by something epsilon, a function of epsilon, basically a power law function of epsilon to a number into L, where L is the length of this boundary. Right. So, suppose I add this term. So, this product state is no longer the exact ground state. Okay. So, I would have some mixing, some superposition. So, if I add such local terms which are right across nearest neighbors, it is going to generate some entanglement between spins which are nearby, okay, in a gap state. That is what happens. So, basically, if I think about these two spins both inside this shaded section, there is some entanglement, but when I do the integrating out of A bar, both these spins remain. So, that entanglement does not show up in the entanglement entropy. Same for two spins here, where again both of them get integrated out, so it does not matter. But think about one spin here and one spin here, and it is across the boundary. Now, I am integrating out one and not the other. So, just like in this two spin problem, this would contribute to some entanglement because they are now entangled, and the magnitude of entanglement is wholly because of this term. If I put this term to 0, then there is no entanglement because this is the exact ground state. Okay? So, there are two things. First of all, how many spins contribute to that entanglement? The number of spins is equal to the number of spins across this boundary, roughly, for big enough boundaries. It scales. So, that is this L. And the fact that when I take this to 0, I should get 0 gives me the power law. I cannot tell anything about this number. It is an even number usually. Okay? So, that is, yeah. Huh? Yeah, all kinds of things can happen. You can have transitions and things like that. Epsilon is much smaller than the gap. Okay? So, you can have phase transitions. Yeah. 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 No. So, okay. So, let me just repeat. So, I was framing the problem in that way, whether I can adiabatically start from one state and adiabatically deform it to another state without closing the gap. But this way of asking the question is extremely ill defined, because how many paths am I going to check? So, what I am trying to do is to propose a measure which would which in this case would tell that I would never be able to go from this ground state of that Hamiltonian to ground state of this Hamiltonian without closing the gap. Okay? And that measure turns out to be entanglement entropy, which is why I am immersed in this calculation. Okay? So, yeah, those are harder questions. I don't even know how to answer those. No, that's what I said. Things which are inside do not contribute to the entanglement entropy, because I am not integrating these spins. Okay? Things which are only across this, at least for local interactions and gap states, that is what happens. Okay. So, basically, if I start with this Hamiltonian and slightly deform this is what I would get. Let us now ask for this. Okay. What happens if I calculate the entanglement entropy using that Hamiltonian? So, now I am choosing this state. Okay. So, what I will get is some number into L. That part comes from the fact that there are these loops. I express this thing in terms of loops. Okay, and these loops. So if you think about two spins sitting next to each other, and it gets contribution. So one on the inside this and one outside. There are various contributions where both of them are up, both of them are down. One is up, one is down, and the other way around. So there is some measure of entanglement between these two spins in this ground state. And that's again local in the sense that that is only true for spins inside and outside. So that gives rise to this term. Okay, there is some number and again a perimeter, but that's not the whole story. There seems to be a number negative. In this form, the gamma is positive. There is this number which comes out. Okay. Now this number turns out to be 2 log 2. Okay. And let me explain log 2. Okay. So this wave function looks quite arbitrary. I mean, each spin is doing whatever, sometimes up, sometimes down, coming from different states that I superposed. So it looks completely arbitrary. But there is one important information in this wave function, that all loops of down spins are closed loops. That's why I call them loops, right? There is no contribution coming from these things where the down spin starts from here and ends here. There is no such state contributing to the ground state. So if I look at this, if I try to draw different states that are contributing to this, basically draw this in full hand, then the loops of down spins are either completely in this, or they cross the boundary. Okay? So whenever they cross the boundary once, they have to come out. Okay? Because it's a closed loop. And that information is built into this wave function, the fact that it has closed loops. Okay? That one qubit of information, if I had loops of one kind, that has a log 2 entropy, and that information I already know. So that cannot contribute to the entanglement entropy, and I need to subtract that out. This 2 is a bit more subtle to explain, and I'll come to that when I discuss the gauge theory, hopefully. So that's this contribution that you need to subtract out. And it's negative. All these things make sense. Okay? That's the qualitative way of understanding it. You need to do a more concrete calculation to do this, to get this numbers out. Yeah. Yeah, there are other terms. These are, I'm writing down the most important terms. Okay, you have to do a much more complicated calculation to isolate some of these terms, and I think there are several concrete proposals, but the most concrete one, as far as I know, are by Wen and Levin. Then this is PRL 2006. Yeah, yeah, negative constant. Okay. Yeah, yeah. I'll come to those things in a moment. So, yeah.
Why don't they use the L squared term also, because they can go through the full volume?
Yeah, so that L term, as I said, is coming from the fact that in this, there are, so if I focus on this spin and this spin, so you understand that I don't need to take spins which are inside or outside, because yeah. Yeah, but the entanglement comes from the fact that if I integrate once a part of it and not the other, right? So basically, there are more complicated, slightly more complicated issues. Let's try to think about this. So this I want to integrate out, and this I want to keep. So if I go through these terms, okay, there would be certain states where both these things are up. Okay. Yeah. So that's the reason why it contributes, and also the fact that it's gapped. Those are the two main ingredients that goes. If it was gapless and these large loops, then I'll be in trouble. I would have other corrections. Okay. Yeah. So there are, if I look at all these other states, all these states contributing to it, and think where these loops are, these loops can either be completely in A bar region, like this loop. It can completely be in region A. So this I think is not a good, but it's, and then there are loops which cross the boundary. The fact that these loops are always closed, it means that if they cross the boundary once, they must cross once more to come out. Okay? So the number of crossings cannot be an arbitrary number. Okay? It has to be an even number. And that is one qubit of information that I know about this ground state. Okay? This ground state already encodes that information. And that's basically the reason why that cannot contribute to this entanglement. Okay? So I get these, and this is the difference. Now, it's harder to say anything about perturbing this model regarding this calculation. But if I add other terms, just like I added these terms, this number would start changing, just like this number started changing. Okay? But this number would not change unless I close a gap. Okay? These are all infinite systems. Yeah. Yeah. Yeah, let's not go into those things. Yeah, there are a whole lot of things are known and a whole lot of things are not known. Okay? Yeah. 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 No, this number would change, but this number is related to that number. Okay? The fourfold degeneracy and things like that, these numbers are related. Yeah.
Sorry, so the degeneracy is 4 to the G.
Yeah.
Here, if it's 2 log 2, does it have any, is it function of G? Is it G times 2 log 2 or?
I actually don't know that answer. Yeah, I have to think. I don't know the answer. Okay. So basically I can add terms like this Ising term, and this term doesn't change. This term of course changes just like this term. Okay. So the point is that there is this negative contribution which seems to be robust. Okay. Now, if I didn't have this negative contribution, I had this kind of contribution only, then I can adiabatically continue the ground state for starting from epsilon some small value to epsilon equal to 0, and my ground state would continuously move to continuously deform into a product state, okay, with 0 entanglement entropy. But for this entanglement with this minus sign that someone asked, this entropy is always a positive number. Okay? Cannot just allow this term to go to 0 and write down a product state. Okay? So that this number prevents it from going into a product, deforming this state into a product state. Okay? Yeah, exactly. So all these are extremely, I mean, the important things are sort of explained. Okay? So this is the reason. So once you cannot adiabatically connect this state to a product state, cannot really deform this state to this state. Okay? Because if both these states can be deformed into a product state, they can be deformed into each other. Okay? So that's basically one idea of one measure of how to state these ideas very clearly. Okay?
But if you have two states that either of them is a product state, then you could not.
Yeah. So then I have to look at what is the value of these things.
But even with the value, maybe different states.
Yeah, I'll have to do more work. I have to do look at the entanglement spectrum and things, quantum numbers of these. I have to do more work. But this way of trying to get some measure out of entanglement seems to work for a large class of systems. Okay? I mean, it's a different question whether this is going to be the only measure or not. I mean, we don't know. Right? Yeah. No. Yeah, so those are related to degeneracies and things like that. Yeah, yeah. That's why this is called the topological entanglement entropy. So this represents an obstruction. This non-zero value represents an obstruction of deforming the ground state to a product state. That's what it is. So this makes the problem more quantitative. Okay? I can now go and calculate this number. Many a times it won't work, but on some occasions it would work, and then I would know that I'm dealing with a very non-trivial state. Sorry? Constant terms? Oh, so you're thinking about this? Yeah. So you're saying about this? Okay. So basically, I don't know. This number can be 4, can be 8. It has to be an even number. So I know only one qubit of information. If I knew the exact number, if the ground state had that information, then I had to subtract the whole information out of it. Okay? Yeah. A huge negative number. If I knew that the number of crossings would be 500, I would have to take that entropy out, right? Take that information out of that entropy. But I know this ground state doesn't know. Okay? Okay. When I started, Kedar, who is not here, told me that I have enough lecture material for 10 lectures. As always, Kedar is right. So, sorry. Okay, so let me quickly, so I covered the non-trivial part. The rest is pretty simple, this excitations. So I create this electric charges using, maybe I am using a different notation, S1, S2. which is product of sigma z I runs from S1 to S2. Okay, so I want charges here and here. So I draw a line. I take the product of all sigma z operators. That creates two excitations of this kind here. And similarly for okay. So I can create this, and as Diptiman explained, these are bosons but have a mutual semiotic statistics, which is like the Aharonov-Bohm phase when I take an electric charge around a magnetic flux, and this is why they are called electric and magnetic charges. Okay? And then there is no reason to call one electric and the other magnetic charge. We all know about electromagnetic dualities. So you can take Maxwell's equation, rotate them, and what you know call electric charge becomes magnetic charge, and all those things. So there is a duality going from E to M. This electromagnetic duality, Jackson. Okay. So fine. What else do I need to cover? Right. So there is also this issue of topological degeneracy, that if I put this on a torus, okay, I can write down various loop operators. Okay. So this direction I called x direction, and this direction I called y direction. So in the x direction I can define x as product of sigma x going along this loop, and z x is product of sigma z going along this loop. And similarly for the y direction, and they form a closed algebra with ground states given by plus, 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 minus, minus, plus, and minus, minus. Yeah. Say that again. Sorry. Can you speak a bit loudly? I cannot hear. Yeah. If both of them have an area law and there is no topological part, yes. At this level, without using symmetries, yes. But that question is much more subtle. Okay, I can. Yeah, I don't. So if I don't have any symmetries, the answer is yes for a class of state. And similarly, on the y direction, I have these 4 ground states, which is like threading flux. Okay. So, any more question about Tori code and the kinds of things that you have seen? Yeah, I have. I would come to gauge theory and explain the two. Okay, hopefully. Okay, so we all are experts in Tori code now. Good. So I'll basically try to reformulate the problem in a way that is much more general, so that all these results can be applied to things. Things where there are no exact solutions. Okay, so let me write down maybe. So this was my Hamiltonian. Okay. So this has gone sufficiently dirty, but if I apply sigma z operator on this side, I would create electric charge here and here. So sigma z operator creates two electric charges. Okay. And similarly, sigma x creates two magnetic charges. Okay. So let me define new set of operators, which so basically what happens is that in general systems of this kind of long-range entanglement, long-range entangled systems, it seems that the things that are robust are emergence of this electric charge and magnetic charge type of operators, which turns out to be anyons. Here they are mutual semions, and it is very useful to have a formalism where I can capture these excitations easily. In this case, writing it in this way is it's a shorthand, but it's really 4 spin operators. So it's a complicated operator. I want to write it in a form try to simplify this. So what I do is at every site I define a Ising variable to state. Yeah. Right. So the point. Sorry. So this I did and did not. The point that you cannot get rid of this log 2 by small changes. It's robust. Okay. Any local perturbation does not change it without causing a phase transition. That and you cannot basically because of that part you cannot deform it to a product state. It means that inherently you have a non-product state. That's basically the signature of long-range entanglement.
It's not the same as if I had an L square, then that would it be a long-range entangled state, or in the improportional term, if I had a thing proportional to L square,
Yeah.
would that also be a long-range?
That's a generic feature of all states. I mean, this is a very particular, L is a very particular feature of a ground state. Okay. So I'm at this moment talking about ground states. So if I take an excited state and try to calculate entanglement entropy using this, generally I find L square, and there is a reason there are propagating modes and things like that, which is why it's L square.
That is also a signature of long-range entanglement, or?
Not necessary in the way that I'm talking. It's, yeah. Okay. So basically on the sides, I define new Ising variables, mu I, which is -1 when there is an electric charge is equal to +1 when no electric charge. So this is, I'm just defining these quantities. Okay. So if that's true, then electric charge creation operator has to be mu xi, which basically anti-commutes with this operator, this Pauli algebra, which changes from -1 to +1. Okay. So then this mu xi is the electric charge creation operator. Same for the annihilation operator, because creating twice is annihilating for Ising charges. Okay. So so now we know that sigma which sits on the bonds creates two electric charges on the two sides that are sharing the bond. So one guess would be basically connect the connection between, so you want to connect these APs, AS and BPs in terms of these new variables. To do that, I need to connect the sigma operators in which AS and BP are defined in terms of those with these new variables. Okay? So then so now I'll use bond indices. So this is one guess. Okay? So I operate this on a bond like this. This is I and J. So I create two charges here, or if there was a charge, I annihilate this. That's a guess. Okay? But this turns out to be not completely correct because of the reason that could have used here instead of mu minus mu x I and minus mu j. Okay? But the sigma operator remains the same because product of two minuses gives me 1. So there is a degree of freedom that I have in defining these mu x operators. Okay? So the right thing, it turns out, is not this thing, but the following operator. So I have two electric charge creation operator and something on the bond denoted by rho z, and this is again an Ising variable. It can take values plus and minus 1. Okay? With this mu x, if I change mu I x to epsilon I mu I x, where epsilon is I is plus minus 1. Okay? And at the same time, I take rho I j z going to epsilon I rho z I j epsilon j. This can be independently plus or minus 1. This sigma does not change at all. So my physical operator that I started out with, when I try to write it in terms of these mu operators, this extra rho operator is imposed on me. Cannot really get rid of these rho operators. Okay? If I do this, I would encounter all kinds of inconsistencies. I have to keep track of how to do things. Because if I encounter minus mu x, I do not know whether it produces minus sigma x or whatnot. Is this clear why this rho operator is imposed on me? Okay. So now let's come to this. So then sigma x. So let's now try to write down this BP operator. I, J, K, L. Okay. So I write mu x I rho z I j mu x j for this bond. This is what this rho z operator is, which is the BP is a product of rho z operators. And then I write down mu j x rho j z rho j k mu k x. So you see that this squares to 1. Okay? All operators, all mu operators occur twice and squares to plus 1. Okay? And this at the end of the day becomes product over rho z ij operators, where ij belongs to this link in this bucket. That's the BP operator. Okay? Now let's come to magnetic charge. Okay? So sigma x creates two magnetic charges. If I act sigma x here, it creates magnetic charge here and here. Okay? And then BP is this. So how do I flip? So I have rho here, 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 and here. Suppose I want to create magnetic charges here and here. In this language, I know this is rho x. But here, how do I do it? I basically introduce another operator, rho x ij, which again anti-commutes with this rho z, and that basically flips the rho z on this link and creates two magnetic charge here and here. Okay? So basically, my sigma x ij operator is equal to rho x ij operator. Okay? And finally, so this is done, but now comes a problem. Suppose I had n sites, and so then there are 2n links. There were 2n sigma variables. Okay? So is it clear why? So there is, to every site, I can uniquely attach 2 links, this and this. So if there are n sites, there are number of bonds is n side by 2. Sorry. Okay. So then there are that many sigma variables, and the dimension of the Hilbert space is 2 to the power 2n site, because at each bond there were. Okay. Now let's come to the mu and the rho variables. At each site there is a mu variable. So there are ns mu variables, and on each bond there is a rho variable. Okay? So there are 2 ns rho variables. So written in terms of these degrees of freedom, the Hilbert space is 2 into 3 ns. Okay? All these are Ising degrees of freedom. So by using this, this looks to be a very bad thing to do, because I now have, so these extra states, there are 2 to the power n extra states which are not describable in terms of these sigma degrees of freedom. Okay? So what's happening? So what's happening is basically the fact that all these degrees of freedom are actually not independent, and we can see that, where is the, as follows. If we look at the AS operator, which is related to this mu z operator, so AS equal to +1, and AS equal to +1 is same as mu z equal to +1, and same for -1. But if I look at the composition of AX operators, so sigma, product of sigma x ij, ij coming from j belonging to I. Okay. If I take the product, it's a product of the 4 row x's coming out of this site I. but that's nothing because that's what AS is. And how many such constraints are there? For every site, there is such a constraint. And this constraint reduces the value of the number of independent degrees of freedom when written in terms of these mu's and rho's. So, then there are there are 2 to the power 3n s, but there are constraints at every site which does not allow you to access and work out the number of things that obey the constraint turn out to be the same. Okay? So, basically you can use these degrees of freedom provided you obey this constraint. Okay? So, why is this more useful, okay, than using these things? So, the understanding comes from trying to understand what these constraints and new variables mean, and that is what I do in 10 minutes, and we will be done for today. Okay. So, mu z is the charge number, okay, or in other words the charge density. Okay. If mu z is 1, there is no charge or the charge density is 0. If mu z is minus 1, the charge density is 1. Okay. So, this is like the charge density. So, I should not write equal to density. Okay. Or in if just to connect it up with Maxwell, it is like rho in Maxwell's electromagnetism. Okay. On the other hand, if you are thinking about this, it changes the charge density. You have a charge here, it makes it hop to the next site. So, these are like charge creation annihilation operators. These are like if I had charged electrons, these are like the C and the C dagger operators on different sites. Okay? This mu x. Okay? Just to tell you things which you might be more familiar with. Okay? So, these are like this operators. Now, what is rho operator? Okay? So, we know that magnetic field, actually magnetic flux, okay, is if it is constant throughout the surface, it is B into A square type of thing, where A is basically the area. So, there is no formal distinction between flux and magnetic field once this is true. Okay. So, now this can also be written as this is a vector potential. Okay. And so, this on a lattice is nothing but sum of A I j, where this is I j k L over a closed. I am discretizing this integral. Okay. So, so here in Maxwell's equation, we know that A can be a real valued field. Okay. But suppose A can only take values 0 and pi. Okay. We just restrict them to take 0 and pi. In the formal sense, I am restricting the gauge group to be a Z2 rather than U1. Okay. So, then if I think about operators which are like e to the power I A I j, if we are working on lattice, I think you remember that hopping term in presence of magnetic field is something like this. Okay. So, this e to the power aij is, so if this is 0 or pi, this can only be plus or minus 1. Okay. This is what our rho variables are. That is here, and this term is nothing but a term similar to this. Okay. And this term is nothing but a term similar to this. If I think about taking product of e to the power I aij, okay, which is equal to e to the power I. So, this is the magnetic flux term, okay, whereas this sigma z is the hopping term in presence of magnetic field, and I have to explain rho x. So, rho x anticommutes with rho z, which is rho z is like the vector potential. So, from things like quantizing electromagnetism, do you know what in this Maxwell theory, what has a non-trivial commutation relation with the vector potential? So, just like p and x has are canonical conjugate and you quantize them, it's electric field. So, this and also changes. So, rho x here is nothing but like the electric field, okay, again e to the power I e. So, then this constraint is like you take the electric field in this direction, this and this, okay. This is, and this thing is nothing but the divergence of that electric field. Again, you raise things to e to the power I e, and we know that things like Gauss's law says that the divergence is nothing but the charge enclosed. So, if there is a charge enclosed, then mu z is minus 1. So, there is a definite physical interpretation to these new variables and their constraints. Okay? So, basically what I will show in the next class, that is tomorrow, is starting with these variables, how to get some more information, complementary information about the problem, which I claim that they are generalizable, but let us see how much I can actually show that they are generalizable. Okay, that is where I would end today. Questions?